So I'm now the chair, I guess, of the next session, which is starting at 2 o'clock right now, and we have some issues with the speakers. One issue is that the last speaker will not be available, so the session was reduced to 2 speakers. And I'm just reading an email from the first speaker saying that, I've just read it to you. I just ran into a major computer attack, a virus attack. Can't use my laptop. Can I go last in the session? My apologies for that. Thanks, Venkat. Okay, so VenkatVenkatasubramanian, the first speaker, has problems with his computer and he cannot run it now. So I think because of this kind of unexpected circumstances, I think we should start with a talk by Yunus Kinhabwala, and he would have at least 30 minutes because there are only 2 speakers for this session now, so each one 30 minutes. So I suggest that Yunus will start now, we'll talk for 30 minutes, and then we'll see if by that time Venkat will be able to connect his computer, and so we'll have Venkat after that. Okay, I suppose that's fine, right? So I'm Venkat, are you ready to present in principle now?
Yeah, actually okay. I can go.
Yeah, so Venkat, go ahead.
Yes,
sorry,
okay.
Yunus, you'll be a second.
Again,
okay.
Can you guys hear me okay?
Yes.
Okay, again, my apologies. I didn't expect this problem to occur, but it just attacked me. So let me just share the screen. Hang on a second. Go here. Right. Good. Okay. Post that. Good. Okay. So, so my talk is at the intersection of thermodynamics and economics, and this is some work we've been doing for a number of years. And Victor has actually heard this the version of this talk about a year ago when I organized a conference at Columbia University on income inequality and entropy and fairness. So, so this is basically the application or developing thermodynamics-like approach to the problem of income distribution, and I call this framework statistical teleodynamics. It is takeoff on the term statistical thermodynamics. Now, in thermodynamics, as you know, the dynamics of the agents are determined by thermal agitations. And now in teleodynamics, this is a generalized version of thermodynamics that is applicable to economic systems. The dynamics of agents, here the agents are rational economic actors, such as Homo economicus, for example, such as people who switch jobs in search of better utility, better salary, and so on. There, the dynamics is driven by their pursuit of goals. And in Greek, telos means goal. So I call this approach teleodynamic approach because here the dynamics of the agents are driven by goal-pursuing behavior, as opposed to thermodynamics of molecules, where molecules switch states based on thermal agitation. So we all know that there is a lot of concern about income inequality and wealth inequality, and here is some statistic that has come out of the work of Thomas Piketty, Sayes, and Guzman, and others. So here is the top 1% share of the income in the US, and it went up from a low of 13% in 1982 to 18% in 2012, actually approaching 20% in recent years. And similarly, the wealth share of the top 1% went from 20% to 42%, approaching 50%. Now, this has created a lot of discussion, as you know, for the last 5 to 10 years. And Occupy Wall Street was the reaction to this sort of economic inequality, extreme inequality. And World Economic Forum in Davos actually identified this economic inequality as the #1 global challenge that we are all facing, even ahead of climate change. So it ranks up there, as you know. Now, the thing about inequality is that we cannot really address this without addressing the issue of fairness. These two things go hand in hand. And I know fairness is a tricky concept, but it cannot be divorced from inequality for our convenience because we want to sidestep that issue. And moreover, behavioral economics work, various kinds of experiments and so on, have shown that people do care a great deal about fairness. There's this work by Bloom out of Yale, and that people actually don't want equality, they only want fairness. And there's this well-known survey by Norton from HBS that how much money that should CEOs be paid. And this was a global survey they did where the results are quite striking. And the ultimatum game is another example where we see that the fairness issues matter. So there's even economic work recent years suggests that we have to address this issue of fairness. Okay, so the question is, how do we handle this mathematically? Okay, so let's not shy away from asking the hard questions, such as how much income inequality is fair in a free market society? By the way, what is fair inequality? Can we even define it mathematically? And what income distribution we ought to see in an ideal free market society? And finally, can we develop a mathematical theory to address these normative questions quantitatively? Now, this is the work I've done in the last 20 years or so, which got published a couple of years ago, actually 3 years ago in 2017, as this book where much of the details are discussed. So this talk is a very, very short summary of what I've talked about in this book. So is inequality per se bad? Not necessarily, for the following reasons. Because different people have different abilities in a society, and so they make different contributions, some more, others less. And so they should be compensated unequally. We understand it. Intuitively, instinctively, we get that. Okay, for example, if John works for an hour and makes $100, and if Lily does the same job and produces similar quality of work, but works for 2 hours, and she earns $200, is there income inequality? Of course there is. Lily got 200 and John got 100. So there is inequality. But is that inequality fair? Of course it is fair. Lily got more because she contributed more. So we understand that. So it is not inequality that people object to. People object to only unfairness. For example, if Lily worked for 2 hours and paid $150, then Lily would object by saying, why am I not getting 200 and I'm getting 150? So it is the fairness part. And similarly, if Lily got 300, then John would object by saying, how come she's getting 300 instead of 200? So it's really not the inequality, but it's the fairness. So basically, by paying Lily 200 and John 100, both are getting paid the same effectively once you adjust for their contribution. So their incomes are not equal, but equitable. So this is what I mean by fair inequality. Now, that was a very easy example, but how do we enforce this fairness in a free market with millions of rational agents buying and selling their products and services? Okay, so is there a measure of fairness in general? And secondly, is there an income distribution that ensures that the same effective economic reward for everyone, just like the John Lilly case? Now, given the complexity of the free market, you would think that the answer is no, and most people think so. But you would be surprised to know that the answer actually is yes. These things can be approached mathematically, and that is basically the work I have done. So let me introduce the ideal free market I'm starting with. We can relax some of these assumptions later on. So we have a large number of employees so that no single employee dominates. A large number of companies, so there is no oligopoly, there is no market power, no rent seeking. These are standard assumptions we make in economics. And the population has a continuous distribution of skill levels. Different people have different endowment of skills. And the skill availability is neither scarce nor abundant. That means there's moderate level of scarcity. That is, you have to pay somebody to get them to work for you. And there is no bias of various kinds. And it's not valid for startups and entertainment stars and so on. So in this economy, consider this company, which I call Chip Tech. And there are N employees. M is the salary budget. Let's say if there are 1,000 employees and 100 million is the salary budget, then the average salary is 100,000. Okay, now different employees make different contributions. For example, janitors keep the premises clean, secretaries schedule appointments, answer phone calls. This is a computer chip company. There are designers making high-end graphic, NVIDIA kind of GPU chips, and which are in great demand. And of course, the senior management is developing a winning market strategy, manage the accounting and finance properly and all that. So different people are making different contributions, and they should be compensated differently, some less, some more. But suddenly the company announces an egalitarian policy. So the CEO calls everybody for a town hall and says, guess what, from tomorrow onwards, everybody is going to be paid the same salary, $100,000, which is the average salary. From janitor to CEO, everyone gets the same money. This has a Gini coefficient of 0 because we believe all people are equal. Okay, so the distribution is no longer a distribution, it's really a delta function at $100,000. Okay, now this sounds great from a social justice perspective, perhaps, but most people would say that this is clearly unfair, particularly for those who contribute more. So what happens to this company after such a policy is declared? Well, those guys who are on the right-hand side of this distribution, that is the senior chip designers and the VPs, executive VPs, and the CEO and so on, who could potentially get much more money than $100,000, they will all threaten to leave. They will protest this unfairness in pay, and they say that they'll leave chip tech for other companies. And in order to keep them, if they leave, the company will simply die. And so despite its noble intentions, it will simply have to pay them more in order to compete in this free market environment. And so they will all be paid more money. And so this distribution will no longer remain stable as a delta function, but it will begin to spread to the right. So this will happen. But what about the guys on the left-hand side of the delta function, say the janitors and the secretaries who are making $100,000? They're not going to protest and threaten to leave. They're making 100K and they're happy with it. But secretaries and other low-level staff in other companies who are making 30K, 40K, 50K, they will look at these salaries and call up the CEO and say, guess what? I'm making $30,000 here as a janitor at this company. Pay me, you don't have to pay me 100K, pay me 35, I'll come and work for you. So the competition from others, from the other companies, will then force this salary to go to a spread towards the left also. And so the distribution eventually begins to evolve like this. This is the dynamics and evolution of the delta function distribution that is unstable, and it leads to this. Now a whole bunch of questions arise. Will this is a self-organizing dynamic. People are making decisions on their own. Will it remain, will it settle down in some particular distribution, or will it keep spreading and contracting, oscillating, or whatnot? Or will it reach an equilibrium distribution? That's question number one. Or if there is an equilibrium distribution, then what is it? And what are the conditions? How do we determine it? And finally, is the equilibrium distribution fair? So these are the questions we will answer, we'll see the answers to in this talk. Now in this, let me also introduce a new economic species. I call this Homo Aestimatus. This is a much more modest sibling of the superhuman rational agent that is assumed in neoclassical economics, the Homo economicus, who is capable of doing all kinds of wonderful things. She's perfectly rational, has perfect information, can compute probabilities of very unlikely events accurately, can calculate complicated utility functions, can discount utilities over various time intervals, and perform amazing mental feats of mathematical gymnastics to maximize expected utility function, and so on. So these are all the things one normally attributes to Homo economicus in neoclassical economics models. Now my guy is a little more modest. Homo Aestimatus is closer to ordinary humans in capability. This agent has modest abilities to make some ballpark estimates about various outcomes, build approximate models, and use heuristics to make decisions. And people do this all the time. People use such approximate techniques in negotiating the price of a car or the price of a home or the salary of different offers, which one they should take. So this new avatar, in some sense, is similar to Homo heuristicus that Gigerenzer had proposed some time back, but this has some new features in addition to this, which I don't have the time to get into. Anyway, so from the Homo Aestimatus perspective, what is the economic utility of a job? Okay, so now the utility is a complicated function, depends on all kinds of parameters and variables, but Aestimatus makes very simple models in evaluating different job offers she has from different companies. For most people, the utility is dominated basically by two pragmatic features. One is that the salary from the job helps us pay the bills now. So there is the immediate utility of the present utility. Then it also gives us a fair shot at a better future. That is, one hopes from this job, working at this job for 2 years, one acquires some new skills. With that, they will get promoted in this company to a better job with a higher salary, or leave this company, go some other place with a better job or higher salary. So essentially, it's a path for upward mobility and to a better and better economic future. So this is a simple behavioral economics-like model that I'm proposing. And I say that, that this effective utility, H sub I, is made of three factors. One is the utility from income. This is the utility from salary, U sub I. V sub I is the disutility of the job. That is, you have to show up to work every day in order to earn this income. So you have to subtract that. And then this W is the utility of future prospects. So that's the future utility. And so the effective utility is made of these three. And notice that this utility function, I call it effective because it accounts for the contribution. The contribution is subtracted here. So this is the effective utility function. So now let's put some more math behind all these things. The utility from income has a diminishing marginal utility feature, and that is, we can model that as logarithmic salary, which is a standard technique. And then now if you consider the net benefit from a job, which is U minus V, as you make more and more salary, U increases. As U increases, the net also increases initially. But eventually, you are spending so much time in order to make more and more money, working overtime, missing time with family and job, job stress causing poor health, physical and mental health, relocation anxieties, you travel a lot, maybe there's toxic work culture. So in order to make more and more, the utility actually keeps going much more rapidly. And eventually, this net benefit has this inverted U. That is, up to a point, you are gaining more and more benefits. After that, it comes down because this term is increasing much more quickly than this term. Now, the way to model that in a simple way is a quadratic function. And so AU minus BU squared will capture this behavior where A and B are some arbitrary positive constants. Now, since U goes as salary, then U squared will go as salary, log salary squared. U goes as log salary, and so U squared goes as log salary squared, and that's the V term. So now we have U and V determined. Now let's determine W. Now, imagine that there are N employees, say in a midtown law firm in New York. These fresh graduates from Columbia Law School have been recruited. And then that on the first day, the managing partner gives a pep talk about how great the firm is, how they're all going to do. And in that process, he says that, well, you know, there are about 100 people say gathered, and he says that one of you will make partner in 7 years. So, the percentage of people making partnership in a top law firm in the US, in Manhattan, is about 2 to 3%. So, essentially, of the N employees, one of the N will make it to the partnership, and once she becomes a partner, she stands to earn $2 million over the life of the partnership. So the expected value of this future prospects, let me go up here, the expected value is a Q over Ni, and so the utility is log of that, and then the utility of the future prospects, when you take the log of that, it becomes negative log Ni. And so now we have, now note that we are not computing complicated expected utility function discounted over many time periods because people are simply incapable of doing it, and people don't do that. But they do make these kind of approximate estimates about how much they potentially stand to gain and that sort of thing. Okay. So Homo economicus can probably do that, but not Homo Aestimatus. So now, based on this kind of behavioral economics kind of ideas, I have an expression now for this effective utility in terms of salary and the competition, which is n sub I. Now, alpha, beta, gamma are positive constants which weight the relative contributions of these terms, and they can vary from agent to agent. But I'm going to start with a one-class society where alpha, beta, gamma are the same for everyone. And now, let's see. Okay, so the question is now, is there a fair income distribution? How would we even recognize it? Okay, well, remember in that John Lilly example, I said that in a fair outcome, even though John made $100, Lilly made $200, after you adjust for their contributions, they are both paid equitably. John worked for 1 hour, so he got $100, and Lilly worked for 2 hours, she got $200. So once you adjust for the contribution, they are both paid the same, which is $100 an hour. So the effective reward after you account for the contribution should be the same for everyone. That is what is a fair outcome is. So basically, by that logic, an income distribution will be fair if the effective utility that I defined in the last slide, H sub I, is the same for everybody, right from janitor to CEO. That is, HI is the same for everyone, that is equal to some constant H star. And so here the salaries again are not equal, but equitable. So the question then is there an income distribution where H sub I is the same for everyone, and can the free market find it? Okay, so this is where game theory comes in. So we use what we know, people call as potential games. So there exists a potential phi such that it is a gradient of the potential is this utility H. And since we know our H, which is this, I can calculate what that potential phi is, which is this. And so in potential games, there is a well-known result that there exists a unique Nash equilibrium when phi is maximized, if the potential is strictly concave, which it is in this case. So we answer the first question. Remember, the first question was, will this self-organizing dynamics, which leads to the spreading of the income distribution, will it ever settle down? Will it ever reach equilibrium? Now we have the answer. Yes, it will reach equilibrium. It is guaranteed to reach a unique Nash equilibrium. When will it reach it? When this potential phi is maximized. Okay. Now the question is, okay, we know that it will reach equilibrium. What is that equilibrium distribution? Now there we recognize a key insight, which is that this contribution of W, phi sub W to this potential function is really entropy in statistical mechanics. And that's a very important connection as it turns out. And now, based on that, I can actually now look at statistical mechanics and thermodynamics from a game theoretic point of view, which I call as the thermodynamic game. Here molecules are jumping around. Instead of switching salaries, they are switching energy levels. And I can define effective utility-like function for the molecules, which is this. And E sub I is the energy of level I, and Ni is the number of molecules in that state. And this will be the corresponding potential for this thermodynamic game. And then when you maximize this subject to the Lagrangian multiplier constraints, lo and behold, we get the income distribution here, which in this case is actually energy distribution, to be the well-known Gibbs-Boltzmann exponential distribution. So we see that the potential game agrees with statistical mechanics in the limiting case of molecules, which are purpose-free. They are not goal-seeking. And that the thermodynamic equilibrium is equivalent to Nash equilibrium, and that in fact phi is Helmholtz free energy. In fact, we even call it thermodynamic potential. And so these are surprising and deep connections that we didn't know that existed. And it turns out then this molecular utility, or this H sub I, is similar to negative chemical potential. So when there is equilibrium, it's like equivalent to chemical equilibrium, or the chemical potentials are equal. Now switching back to the income game.
You should come into the end, because time is, you should leave some time for questions.
Yes, thank you.
In a couple of minutes,
so,
1 minute or so.
So you can show that this leads to a log normal distribution. And is the distribution fair? If you calculate the H sub I for everyone, it turns out to be the same throughout the distribution. So this is a fair distribution because everyone gets the same effective economic reward the salaries are different, as you can see, but the effective economic reward is the same. So by mathematically, we can prove that this log normal distribution is the fairest distribution that the free market can produce. And one can show that this is actually related to the Lyapunov of stability function and so on. But and this is also the socially optimal outcome. I'll skip all that. So I compute a fairness index, and then we compared my prediction with different countries based on pre-tax income data from the Western democracies. And you can see here that if this is for Norway, if Norway was a perfectly ideal society, then the bottom 90% share should lie across the 0% axis, because I'm measuring the unfairness. There should be no unfairness, so that should be there. But the actual data tells you that the bottom 90% is getting less than their fair share. This is pre-tax wage income data for the last 80 years or so. But then you see that they are very close to the ideal share, on average about 7% less. The middle 10 to 1%, sometimes they make less, sometimes they make more, so they're also fairly close. The top 1%, they do very well no matter where you go, and they make more than 100% of their income tax. So basically for Norway, the bottom 99% of the people are getting more or less their fair income share, and that's Norway. Now, if you look at the US, it's the other way. It's the other extreme, where the bottom 90% has been steadily getting less and less. For 30 years between 1945 to 1975, they actually did reasonably well, but now they are making 24% less, and the top 1% is doing very well, and the middle third is somewhere in between. Every other country is somewhere in between, Norway being the fairest society, and current US is the most unfair. Norway, Sweden, Denmark, more or less the same. Then comes Switzerland, Netherlands, Australia, France, Germany, Japan, Canada, UK, US. We also showed that in a two-class society, you'll get two normal distributions overlapping, log normal distributions overlapping each other. But the second one, the top one, this tail can be mistaken for a power law distribution. And so it explains the data there as well. So I call this framework thermodynamics, as I mentioned. Instead of the two laws of thermo, here we have four laws. And the four laws being the survival postulate, the performance target postulate, optimally robust design postulate, and the maximum entropy design postulate. These four reduce to the two laws of thermodynamics in the case of molecules. So I would like to acknowledge my collaborators, my former PhD student, Dr. Yu Luo, and my colleague here at Columbia in industrial engineering, Professor J. Sethuraman. So as I mentioned, that a lot of this is outlined in my book in great detail, if you're interested. And thank you again for your attention. I'm happy to take any questions you might have.
Okay, Venkat, thank you very much for the talk. Okay, so we're quite kind of almost on time. If there is comes kind of short question, maybe you can take it. I don't see anything on the chat, and I don't see any raised hands. So maybe we should proceed to next talk by Yunus.
Thank you again, Victor.
Yes, yes, and of course you're welcome to contact Venkat, separately, directly.
Of course.
Yeah,
that's Venkat, what's the title of your book? Just curious.
Show the book, Venkat. Show your book. Show your slide of your book.
Sorry. Yeah, thank you. Here it is.
So this is the title. How much inequality is fair?
That's perfect. Thank you so much.
How much inequality is fair? Yeah, that's the book.
Okay, so we got a question. So now I think we'll proceed to Yunus's talk, Yunus Kin Habwala. Okay, so thanks for Venkat, and let's proceed with Yunus.